Today's lesson is brought to you by the letter R. R for rates. So you know how in your sort of chemistry academic career so far, whenever your teacher talks about a chemical reaction, it's been assumed that as long as your two reactant particles are electronically compatible, then of course, boom, bang, pow, magic happens, and as you guys always hope, there's going to be a chemical, there's going to be an explosion of some sort. Well, that's true and that's not true. So electronic compatibility is still very much the star. It is what is definitely required to even get a reaction to even possibly proceed. But there are definitely other factors that are involved. Chemical reactions are kind of like, I kind of like to equate it to kind of like a bad teen soap opera, right? There's actually a lot of drama that goes on in between before your two reactant particles actually go ahead and bond and make the products. So the question becomes, what are those other conditions that are required? So today we're going to look, or in this unit rather, we're going to look at all of those factors that A, initiate reaction, so meaning what are the conditions besides electronic compatibility, of course. So what are the other conditions that allow your reaction to even begin to react? And then, once you've gotten it to react, what if you have a really slow reaction? So it does go ahead, but it's taking forever. So the second question that we need to kind of figure out or answer is, okay, I've got my reaction to go, it's taking too long. How do I speed the reaction up? Okay, so in this unit, which is talking strictly about rates, meaning how quick or how slow a reaction proceeds, we're going to look at two major ideas. So the first major idea that we're going to be focusing on is how to initiate a reaction. So meaning, how do I kind of get my two reactant particles to kind of come together and get it to even begin to react. Okay, so kind of kick it in the ass to get it to even begin to react. So that's the first step. The other big component that we're going to look at in this unit is, okay, once I've gotten it to react, how do I then go ahead and make it go faster if it's not going as quickly as I would like it to? Okay, as we've just mentioned earlier, we've talked about the idea that so far in your academic career, you've always assumed that if you have two particles with electronic compatibility, so electronic compatibility, then of course, you assume magic will happen, reaction will happen, and the reaction more or less in your mind will always be instantaneous, meaning it will happen quickly and it'll be done. Now, once again, I cannot stress enough that electronic compatibility is still very much the main star. If without that, you're dead in the water. Your reaction's not going to go at all. However, there are many other supporting casts that are required to make the reaction proceed. So what are those other factors that are required? So the other very important factor that's required is actually geometry. So your two reactant particles there, they have to get together in a correct geometry. So it's very much literally kind of like a jigsaw puzzle. Okay, so the two pieces have to fit properly. Otherwise, again, there won't be a reaction. The other factor that's also very important, and this is important for pretty much any physical process that exists, and that's energy. Do your two particles have enough energy to even, come together, bond, form this product? So energy is extremely important as well. And the last one, this one is a little bit of a no-brainer. It's quite obvious. Do you have enough of your reactant particles for them to react? So if there's too few of them, the chances of them meeting up, of them successfully bonding will be quite slim. So the amount. Do you have enough? Do you have enough of your reactant particles to go ahead and react? Okay, so in terms of initiating your reactions, There are your four big stars there. Electronic compatibility, of course, is the lead actor or actress. And then you've got the supporting cast. You've got correct geometry, you've got energy that's needed, and you've got the amount or the concentration that's needed. Okay. What we're going to do in this unit, as I promised earlier, is that we are going to look at the two big ideas of this unit. The first big idea being, what are the factors that are required to even initiate your reaction? So right now, that's what we're going to focus our attention on. We're going to focus our attention on what are those factors that are required to kind of get my two reactant particles to kind of even get out of the gate and begin to react. Okay, so we're going to start looking at some of these factors here in a little bit more detail. We're going to start by looking at this whole geometry idea. Okay, so if you think about it, if you have two reactant particles, for them to bond, they've got to, quote, meet each other. So in the chemistry world, you know, how do two reactant particles, quote, meet? Well, they meet by slamming into each other, by colliding into each other. Okay, so collision is a very central concept in chemical reactions. Okay, so for your two reactant particles to do anything at all, they must meet. In other words, they must collide into each other. Okay, and not only do they have to collide in a very specific geometry. So they kind of have to fit together like a jigsaw puzzle. Okay, so collision. Geometry is the major first idea that we're going to explore. Okay, and then the other major idea that we're going to explore is what's called the activation energy. So as I mentioned earlier, every single particle has to have enough energy to be able to go ahead and react. Okay, and that energy is called the activation energy, or shortened as EA for short. Okay, so activation energy is essentially the energy that your particles have in order to overcome what's called the potential energy barrier. We're going to talk a lot about what this potential energy barrier is in a few minutes, but right now let's focus on aspect A, which is collision geometry. Okay, so what is this whole idea of collision? So collision essentially is exactly that. So when your two compounds approach one another, they have to approach in a very specific fashion. So here again is where we need some clarification. So again, I think for most students, up to this point in their chemistry career, they've always thought that, okay, well, if my two reactant particles are totally compatible, it doesn't friggin' matter how they get together. I mean, you know, who cares how they get together? They're electronically compatible. They're going to go ahead and form the products. Well, that's not necessarily true. The analogy I always like to use is, you know, kind of like, you know, your boyfriend or your girlfriend. Obviously, you are in a relationship with your boyfriend or your girlfriend because there are certain qualities about them that you find very good or very attractive. But that does not mean that every single aspect about them is attractive, right? So, you know, there may be little things here and there that you may find, quote, repulsive or not very attractive, okay? And that's the exact same thing in the chemical world. Remember how I said it's like a bad teen drama? Well, it is, okay? So in terms of your two reactant particles getting together, it has to be the parts that are attracted to each other that jigsaw together. Okay, so if you get two repulsive parts of your reactant particles coming together, then your reaction is going to fall apart. Okay, so we'll see a visual of that in a second here. Okay, so when your two compounds approach one another, not all of their atoms are necessarily electronically compatible. So there are some parts on that atom that's compatible with his partner, and then there's some parts that are repulsive. And you can guess, surprise, surprise, that it's the compatible parts that must collide into each other. They're the ones that have to meet, okay, in order for the reaction to go ahead and proceed. Okay, so here's a very realistic example here that I'm going to show you. So ethene. So ethene looks like this. as a molecule. If you remember anything at all about organic chemistry from last year, you'll remember that it looks like this. And then it's reacting with hydrochloric acid. So I'm just going to kind of change up the color here, just to make it very, very clear here as to how we're doing this. So there's my HCl particle. Okay. Now let's take a peek at this double bond. Okay, so we do know, of course, from organic chemistry from last year, that a double bond essentially means that you have 4 electrons that are sharing that orbital space there. Well, if you have 4 electrons, essentially what this tells us is that this area here is electron rich, meaning that it's partially negative. It has a partial negative field. Okay. If we look at the HCl molecule here, okay, we can see, again, if you remember back to last year, we talked about polar covalent molecules. You remember that HCl has a dipole moment that looks like this. So what this means, of course, is that the hydrogen ion, or the hydrogen particle here, is partial positive, because the chlorine is the more electronegative species, thus it is partial negative. Okay? So HCl is very much a polar covalent molecule, with the partial positive end being the hydrogen, the partial negative end being the chlorine ion. Okay? Now, if you think about these two reactant particles coming together or colliding, okay, obviously, we all know the fundamental rule of nature. You've probably learned it since you were in grade 3. Opposite charges attract. So what does that mean? That means then that if you have your reaction proceeding exactly as I've drawn it, so meaning that the H atom on your HCl is approaching the double bond in this manner, just like so, this is going to be what we call a favorable collision. Okay, so meaning this is going to result in a product being made. Okay, because what you have here is you have a partial positive atom approaching a partial negative section of your ethene molecule. Opposite charges attract one another, thus we have a favorable outcome, meaning we're going to end up with a molecule that looks like this. So your product will end up looking like so. Now this is what we would call favorable geometry. So in this case, the way that these two reactant particles have approached each other, it's geometrically correct, so therefore a product is made. We'll call this scenario A. Let's take a peek at a scenario B, where you don't have successful collision. So in scenario B, here's what you would have. So we'd have your same reactant particle, and of course, you know, all the usual conditions apply. That double bond, of course, is again partial negative, but except this time, let's switch the positioning of your HCl around so that now it's the partial negative chlorine that's approaching this double bond. Now you can already imagine this guy being partial negative, this guy also being partial negative, so partial negative, and they are right now approaching one another. So what you have is you have a situation like this right now. Now as you can imagine, this is not going to be successful. This is a repulsive situation. And therefore, your reaction does not proceed. There's no reaction that proceeds here, meaning that even though these two reactant particles are electronically compatible, so remember what I said, right? The star of the show is still very much electronic compatibility. So these two guys are electronically compatible, but unfortunately, because they have approached each other in an awkward angle, the reaction falls apart in this case, if you have them coming together in that manner. One last note before I stop today's lesson is talking about multiple reactant particles coming together and bonding. So generally speaking, again, in most of your academic career so far, you've probably seen most reactions as being two reactant particles, forming a series of products. As you keep, continuing on in your chemistry career, you will find that definitely as the reactions get more and more complex, you may have 3, you may have 4, you may have up to 5 reactant particles that are reacting to form products. So how does that lend itself, to rate, and how does it lend itself to how fast or how slow? So just a very quick note, the possibility of a reaction with 3 or more reactants all being able to kind of come together correctly in the right geometry with the right energy and all of that good stuff is really unlikely. So highly unlikely. Okay, oops. Sorry, I gave you the wrong color there for the highlighter. Apologize. So extremely unlikely that it's able to do that. Okay, so in these kind of cases, the types of cases where you have 3, 4, or 5 reactant particles all trying to bond and form products, these are what we call complex reactions in chemistry, and they tend to occur in multiple steps. So they don't just all happen in one step. It's not like, oh, yep, my reactants get together, bam, and here's my products. It doesn't work like that. Okay, so you may need 3, 4, 5, 6 different steps for it to be completed.